So this is the first webinar of our Phidias project. So maybe next slide, Francesco. Okay, so this is the agenda of this webinar. We have 5 presentations of 10 minutes, and we have some question and answer session during this webinar. So I'm starting with the first presentation as a Phidias project coordinator. So next slide, please. So my name is Boris Dintran, and I'm the Phidias coordinator and also the CINES director. So CINES, just one slide on what CINES is. CINES is located in France. The name of the center is Centre Informatique National de l'Enseignement Supérieur. And CINES is one of the 3 national supercomputing centers in France. We are located in Montpellier, in the south of France. We are around 60 people on site with a budget of 10 million euro annual budget. And we provide HPC resources with Oxygen supercomputer. We provide IT hosting for around 20 academic partners, and we also provide archiving services for long-term preservation of data and digital documents. Okay, next slide, Francesco. So let's go to Phidias. So Phidias is a European project that we won last year in June. So the main objective of Phidias is to build a new kind of HPC and HPDA services. And to do that, we did a proposal to the European Commission by answering to the CEF program. CEF is Connecting European Facilities. And this call was devoted to HPC, a new kind of HPC services for European researchers. So the duration of the project is 3 years. We got around 2.6 million euro, which is 75% of the total budget of the project. And the project officer is Marc Vela-Musca from INEA. INEA, it's a European organization that launched the CEF program. So INEA, it's Innovation and Network Executive Agency. Okay, next slide. So Phidias is based on a consortium, of course, and this consortium has 13 partners at that time. 8 partners are coming from France. So you see the partners, it's CINES, CERFAX, CNRS, Geomatis, a small SME, IRD, IFROMER, Neovia Innovation, it's SME also, Spacia, another SME. So there are the 8 French partners. 2 partners are coming from Finland, CSA, which is a national supercomputing center in Finland, something like the CINES of Finland, in Finland. And also another Finnish partner, SHIC. SHIC is the Finnish Environment Institute. 1 partner is from Netherlands. It's called Maris in oceanography. 1 from Italy, it's a Trust IT for communication and dissemination. And 1 partner from Belgium, it's a University of Liège. So 13 partners, a majority of them coming from France, but also 5 partners from European countries. Okay, next slide. So Phidias has 4 main challenges. The first challenge we have is to handling the diversity of data coming from the Earth system research infrastructure. Indeed, our main provider of data in the Phidias project is a research infrastructure called DataTerra. I will show you next slide. So we have a large variety of data in Phidias. The challenge 2 for their data. Challenge 3 is to scale the existing data processing tool towards supercomputers. And challenge 4 is to broaden the spectrum of Phidias in direction of industry and also other scientific domains. Okay, next slide. So as I said, the data are coming from the DataTerra research infrastructure, and this infrastructure has data coming from ocean, from the Audatis data pool, atmosphere from the FAIRis data pool, Theia, the land surfaces pole, and Formater, it's a solid earth pole. And there's 4 poles, data pole, shape the DataTerra research infrastructure. Okay, so Phidias is devoted to the processing of Earth system sciences. Okay, next slide. So the 3 scientific use cases in Phidias are coming from DataTerra. So the first one is scientific use case from the FAIRis data pool, so in the atmospheric sciences. The second use case is coming from Theia, so from the land surfaces data pool. And the third use case is coming from Audatis, so it's for ocean and is led by Ifremer. So each use case is led by a partner. So the use case 1 is led by Spatia, use case 2 by ERD, and use case 3 by Ifremer. Next slide. So if we do well our job, this is what we are supposed to build in Phidias. It's to build a generic and fully integrated workflow. So on the left side of the sketch, you have the data. Okay, so data acquisition from the Earth system sciences. So mainly satellite data. And once we got the data, we can do smart processing or HPC processing using a supercomputer like the one we have at CINES. So there's smart processing and HPC processing are done on a very big machine, on a big supercomputer. Once those processing are done, the goal is to diffuse the data, the metadata, the added values on the web using FAIR principles. So FAIR is findable, accessible, interoperable, and reusable principles. And it is very important for us. We want to diffuse, to communicate broadly our results using the FAIR system. And of course, at CINES, we can archive the data at the end. And this is also one possibility in Phidias to give researchers the capability of archiving their data for a very long term. So this is the generic workflow we want to build in Phidias, from the acquisition to the archiving for very large processing on the supercomputer, and we diffuse our results using the FAIR principle. Okay, so next slide. So the project organization is simple, and typically it's a typical organization European for a European project. We have a technical board, we have a management board, and we have different WP work package, and also we have 2 committees to advise the project, a scientific and user committee and a security committee. So this is typical for a European project. And as you show, next slide, as you see on the next slide, this is the 7 work packages we have actually in Phidias. WP1 is just for the management of the project and is led by CINES. WP2 is for the compute and storage workflow. So this is also led by CINES, and this is the main computing and storage and archiving facilities that will be used by the use cases. WP3 is the technical coordination and is led by the DataTerra research infrastructure. WP4 is satellite data and is led by Spacia, so it is the atmospheric use case. WP5 is for the environmental monitoring, is led by IRD, and it is for land surfaces. WP6 is the ocean use case led by IFROMER, and WP7 is for the dissemination, communication, and outreach. Very important for us also. We want to communicate on this project to the general public, because it's European money, and so it's public money. So we must communicate our results, and we must communicate also on the project evolution. Okay, so and this WP7 is led by Trust IT, the Italian SME. Okay, next slide. Yeah, so that's the last one. So of course we have a website, Phidias HPC.eu. We have also a LinkedIn account and a Twitter account, so you can follow our activities on a daily basis using this communication tool. Okay, so thank you to all participants, and now I will give the speech to Pascal Prunet for
yes, just I'm the moderator of the webinar. There is, Boris, just one question from the audience for you, if you can reply very, very quickly before leaving the floor to Pascal. They ask, how, according to you, how building a prototype for hard scientific data can improve tangibly researcher and scientist daily life?
Yes, a good question. Yes, Francisco. So the main idea in Phidias is to give a researcher the possibility to run their existing treatments that are actually running on a workstation. And so the main idea is to give them the possibility to run on large supercomputers in order to save times, of course, because it's faster, but also to study larger systems. Okay, and this is the main idea. And another idea also for facilitate the life of researcher is to give them the possibility to do that easily. So something like computing on demands based on cloud tools. So we are very inspired by the GAFA for the web giants. So the idea is to just by doing a few clicks, you can start the processing on the machine, on the big machine, and can also disseminate your results using web tools. So normally Phidias will provide easily user-friendly tools to researchers such that they will be able to use very large machine, large computing and storage facilities.
Okay, thank you very much, Boris. So it's time to shift to Pascal's presentation.
Okay, thank you. Do you hear me correctly, and do you have a good view of the slides already?
Yes, loud and clear, and you can go.
Okay, thank you. Thank you, Francesco. Welcome, everyone. Thank you for participating to that webinar. I just would like to give you a brief presentation of the use case related to atmosphere data, satellite data. So aiming at developing intelligent screening facilities for air quality and climate, basically. So this work is performed by Spacia together with ICAR-IRIS, IGEOS, a French company, and SRON, the space center in Netherlands. So just very brief, few words about the Spacia company, which is an independent SME focusing on research and development in space science and environment. We are a young and small company with 11 people at the moment. Our main activity is focusing on atmospheric satellite data, processing, analysis, exploitation, and remote sensing of that sort of data in order to prepare future missions and exploit the present missions. Our main work is to have expertise both on satellite data and on atmospheric science in order to cover all the value chain between the data and the applications. And our main goal would be hopefully to acting for a better use of that data for environment and atmospheric science. So coming to Phidias, our main goal here is to develop processing for the atmosphere issues. So first of all, the context. The problem, as you well know all here, is that we have environmental health problems at different scale, local, regional scale, because of continuous increasing of human activity, impact and modify the atmospheric composition, impacting on environment, health, and economy. So there is strong needs to understand and to monitor these issues in order to act if we can. And on the other side, there is European opportunities because Europe is engineering really in the area of operational measurement of the air composition from space in order to provide forecasting of chemical weather and climate monitoring. This is a very important effort done by the Europe, in particular with 4 new operational satellites, which will be launched in 2021, aiming at observing atmosphere with unprecedented accuracy and coverage, together with capacity for measuring greenhouse gases and measuring human emission. And in parallel to that, there is development of operational forecasting services, in particular the CAMS service, European service, which is aimed at forecasting atmospheric chemistry, and the C3A service for climate. So the challenge from that is that, as already said by Boris, from 2021, but already now, we are faced to an unprecedented amount of atmospheric data, atmospheric information with an improved quality, improved coverage. And of course, there is difficulty to deal with that for properly address all this new available information, unknown information from some part. And the key challenge, for example, in particular, is really to provide the capacity of the in position to identify, focusing the useful data, for example, by targeting atmospheric sands which are of interest and of importance for climate and for air quality. So this is a goal of Phidias. Really, in that use case, is really to develop a screening approach for the exploitation of this large amount of satellite data in an operational context. Just an illustration of the position of the problem. Today we are all these data which are partially at least underexploited or non-used because of the quantity, because of the complexity. At the moment, there is 2 ways to use that data. The operational ways, which is basically represented by operational service like CAMS, who is using operationally all that data with efficient real-time assimilation in modeling capacity for forecasting. But of course, these systems are not able to use all the data, and in particular, they are not able to use extreme data, special data, or not well understood data. So there is a reduced added value with respect to all the available information. On the other side, the research activity allows to focus on specific events, focus on specific data sets, of course, and this is very well adapted to innovate and to look at new sorts of data, but of course, this is a case-by-case exploitation without capacity for exhaustive exploitation, and of course, no real-time analysis. So the idea of Phidias, and this use case in particular, is to propose, develop efficient detection and filtering in real time operationally of relevant data. And this is the main idea in order to provide real-time detection, analysis of specific event, extreme event, for example, fire, high episode of pollution, etc. And in order to provide new insight and innovate, the main goal in the frame of Phidias would be to develop and propose dedicated services like early warning, monitoring, decision support. But of course, this work should support the existing effort for use the data, On the operational side, this will be provide added value in order to verify and improve the use of the data. And on the research side, this will provide the capacity for robust detection, objective filtering in order to be more efficient for the use and the analysis of it. So this is really the goal of that work package. And what we are proposing in that project is to demonstrate that approach by working on Sentinel-5 precursor, which is the first atmospheric sentinel for air and quality and for air quality and climate. Sorry. So this is a satellite launch in 2017. This is the precursor of the next Sentinel for atmosphere, and this provides a lot of information. I will distinguish here what we call the level 1 product, that is the raw measurement of spectrum from the atmosphere. This level 1 product represents a lot of information. There is typically 20 million of measurements per day, representing a huge volume of data, typically 500 gigabytes per day. So this is the direct information, the raw information from the satellite, and from that information, operational processing will allow to derive what we call the level 2 product, that is the geophysical information. And typically, Sentinel-5 is providing measurement of, for example, ozone, carbon monoxide, methane, all over the world each day. So all this information is of very strong interest because this is containing new information and because this is the first guess and the first preparation of the next Sentinel generation. The goal of our project is really to test two types of prototype in order to exploit correctly that data. First, starting from the level 1 information, we would like to develop specific processing based on principal component analysis, focusing on the detection of extreme events. I will give an illustration. And second one, we would like to develop level 2 data processing based on new artificial intelligence method in order to automatically, objectively detect the pollutant plume for their use in scientific or operational processing.
Pascal, just 2 minutes, please.
Okay. Brief illustration for the first one. The goal is to provide real-time operational detection of extreme events in order to be used for research and for operational services. An example here, which is illustrating by the use of YASI data. This is a work already done by Spacia and partners supported by CNES for example, detecting fires, big fires over Indonesia. And this example illustrates the fact that using classical product, which is in the middle of the slide, you have some partial detection of this event, but using principal component analysis, this allows even over a cloud situation to have a full detection of the event and to allow the extraction of useful information directly and rapidly from the level 1 data. And the goal is to apply that processing to Sentinel-5. The other processing, detection of plume, is really to have an objective automatic identification of that plume in order to use for scientific and operational processing. And this is illustrated here by simply illustrating the fact that on the left you have some illustration, ideal illustration of the atmospheric gradient, which could be measured from space, and in particular you can see some plumes, which can be directly related to the emission of pollutant, as an example on the left. And so the idea is really to use the level 2 Sentinel-5 products, which are providing very clear and very interesting detection of plume, as illustrated here, and develop innovative technique in order to automatically identify, characterize, and provide information on that plume. And so last slide is just to conclude on the goal of that use case. The question is really the following: space-based Earth observation will provide an amazing, unprecedented amount of complex informative data. How can we use that comprehensively? Because operational model and system fail to exploit the non-understood data on one side, on the other side, research is really limited to underline all the information. And the goal of Spacia and Phidias in that project will be to provide new tools, approach to deal with that measurement in order really to allow better and more efficient use of the data. And of course, if possible, pave the way for new paradigm in the use of all this new information. Thank you very much for your attention.
Okay, thank you, Pascal. Thank you very much. So, some question?
Yes, we have a question from the audience. If Pascal, if you can, before leaving the floor to Jean-Christophe, we have a question for Pascal. And it says, where enhanced quality screening can lead scientific research in the future? Can you reply quickly?
Yes, okay, well, there is a lot of possible answer to that question, but the main idea, at least in how work, is really to go to a new paradigm again. That is, up to now, we are based our understanding and forecasting of the atmosphere and the climate based on the modeling. And this modeling is constrained by the data. But now we have a lot of data, a lot of new information, and the model are not able to deal correctly with this new information. For example, because some of the processing, atmospheric processing shown or seen by the data are not understood and are not put on the model. So the idea will be perhaps to put the data at the beginning of the understand processing and use the model as some interpolation of the data. So putting the data at the beginning is perhaps the next step for using all that information.
Okay, thank you very much, Pascal. So now the stage is for Jean-Christophe Desconnet for WP5. Jean-Christophe?
Yeah. Hi, everybody. My name, yes, I'm here. My name is Jean-Christophe Desconnet. I'm coming from IRD, and I will present the use case coming from the land surface scientific community. And especially, I present two use cases about environmental characterization and monitoring. Before I will give some words about my institution. My institution is IRD, stands for French National Research Institute for Sustainable Development. We are working primarily in partnership with Mediterranean and intertropical country on the science of global development issue, and particularly we are involved in multidisciplinary research like health, climate change, agriculture, or biodiversity. And I am in the joint unit called Espace Dev, which work especially on interdisciplinary fields and with a strong skills on data infrastructure design. About the challenges, data and HPC challenges for the land surface community, it's very important to know that the land surface community have a shared diagnostic among scientific community and public authorities the last year, and this diagnostic confirms that the satellitary images are underused by the public authority and the scientific community due from several things like difficulty to accessing relevant images, or getting appropriate equipment like sufficient HPC resources or sufficient data storage. It's processing the satellite imagery for the land community is difficult because we should have many skills, very high technical skills. So for us, one of the big challenges is to, for this end user, is to facilitate the selection of images and to facilitate also the analysis activity to provide the the product expected for the monitoring, environmental monitoring. Under this challenge, there are many issues and technical one. The first technical issue is to have the capacity to manage access of the very large amount of images and big images. The images in for environmental monitoring are very high resolution images or high resolution images. The other technical challenges is to have environment, to have scalable environment for Earth observation data processing. And finally, the second kind of issue is to provide the openness and the reusability of the raw data, but also the product data coming from the processing chain. Now, before the Phidias project, the land community are organized through various French national projects to provide the acquisition, the production, and the diffusion of various kinds of images. I give two kind of examples on this slide. A main project called GeoSud are provided today a great catalog of spot images. This is optical, very high resolution images, and the catalog GeoSud provide also images from the Pleiad platform. This is also very high resolution optical images. Another side, coming from the ESA and the CNES, the French spatial agencies, we are available from the land surface community, the TEPS catalog that provide a radar and optical sentinel product around 10 million of raw images. Other work that the land surface community provide the last year also close to the GeoSud project. This is on-demand platform linked to the catalog image catalog GeoSud. We are design and prototype pre-processing services such image extraction, subsetting, segmentation, classification, coming from using the Orfeo Toolbox library dedicated to the image processing. And we want to use this experiment and this prototype to go ahead on the Phidias projects. And finally, about the work, the state of the art on coming from the land surface community around the TIA land surface pole. The Scientific Expertise Center gathering the many work algorithm from the scientific community to propose the design and the production of various mapping around agriculture, forest, urban, coastline, and so on.
Okay.
Well, so I'm not finished.
2 minutes left, Jean-Christophe, please.
Yeah. Okay. The objective of the objective of the work package 5 is to you understand merging scientific experimental algorithm coming from the TIA community and taking advantage of the very high resolution images catalog existing to serve the community user needs with the technical sub-objective providing dedicated environmental application to the target user, open the dissemination of processing chain output in fair way, and also leveraging artificial intelligence technique to provide alternative image classification. I want, before finishing my presentation, I want to show one
slide. Yes, one slide, please.
Yes. Please. A little bit more. I want to present one of example of use case that we want to design and prototype in the Phidias projects. This is the Sentinel. This use case use Sentinel-1 and Sentinel-2 images to produce soil moisture mapping at a plot scale. This is really interesting application because the user targeted are both the scientific community around the water cycle modelization purpose and also the farming sector to help to the mapping irrigation activity. And the second one use case is to take advantage of intelligence artificial library to provide more accurate images from Sentinel-2, optical Sentinel images.
Okay, that's okay?
Yeah, the last one, please.
Okay, last one then.
Yeah, the last one, some words about the architecture, targeted architecture that we want to setting up and designing these projects. The idea is to have an architecture which provide a discovery application to the end user to go to find and to process data services and on-demand processing from notebooks environment or from with interactive web environment. Thank you very much. Sorry for the time. Okay. Thank you very much.
No,
thank you, Jean-Christophe.
It's okay, Jean-Christophe. Yeah, I pick it up from here. It was a very interesting presentation. And thank you very much, Jean-Christophe. Before leaving the floor to Cécile, I have another question from you, Jean-Christophe, from the audience. And they ask, how can it be possible to turn Earth observation data into valuable global information for the EO community, for the Earth observation, I think it means.
Yes, for us, yes, thank you very much. As I said, the difficulty for the land and environmental community is to provide added services from the image satellite. So the challenge for us to turn observation data to global information and usable information for the community is to provide easy to use services coming from the HPC and the storage capacity. So for us, the challenge is to give to facilitate the access to the data services coming from the HPC capacity.
Okay, thank you very much. Now it's Cécile's turn.
Good morning, everybody. Hello, so I'm Cécile Nice. I'm from Ifremer, and I will talk to you about the work project 6. It's about how we're going to use, how are we going to try to boost the use of Blue Cloud services for marine data studies. What do we mean by this? Is that we want to try by combining and collocate data from different sources, mainly in situ and satellite sources. For this, we will try to enhance data archiving because some data cannot be reproduced, and by bettering the archiving, we will facilitate also the reuse of the data. And also we'll try during this ocean use case to speed up the collocation of different data sources. So by colocalization, I mean that that we will try to put together data from satellites and in situ that are in the same gridded area. For the use case, we also try to adopt new data structures, so mainly data cubes, also NoSQL databases, and some semantic web. And how are we going to do that is by using data browsing and processing facilities. We're mainly focusing on two geographical areas, so the North Atlantic Ocean and the Baltic Sea. We have mainly two case studies, so we're going to study the surface salinity in North Atlantic and also chlorophyll in Northeast Atlantic and the Baltic Sea. For the surface salinity, we will try to get data from CTD, orcofloats, and from satellite images. And for the chlorophyll, the same, so CTD, BGC orcofloats, FAIRibox, and Sentinel-2 images. For these two case studies, we're going to use visual comparison while inputting data and outputting data using GIS features. So this will allow us to do some software comparison and processing comparison between what the results are going to be for using Bangeo or more Diva software. Why is there a specific case study on the ocean? It's because the ocean is quite a difficult ecosystem to observe. It's constantly evolving. The sea isn't the same in the winter or in the summer. And you have also more specifically phenomena that are evolving more quickly, meaning hourly or even daily, like waves, currents, plankton blooms. For this, we require the use of several complementary systems. So the satellites, for example, can only detect the few first millimeters of the ocean. So we will need also buoys that are more fixed or traveling buoys, underwater vehicles also to gather more data. And we have the importance also to compare the results we're getting from the different data acquisition. So we will have, as we told you before, two mainly case studies. So for the why are we choosing to speak about temperature and salinity? It's because it's what's driving mainly the ocean circulation. And the chlorophyll is important because it can be an indicator of the primary production and eutrophication like plankton blooms. For this, the data we will aggregate and process is data from the Copernicus Marine Environmental Services, from SeaDataNet, and from EWANET. So here you have a table comparing bits what type of data you have from the different data sources. So for in situ, we have CMEMS for North Atlantic and Baltic Sea, but you also satellite data. For our use case, we will try to improve the data storage, as I told you before. Where do we need to improve this? Because at the moment, it's not very efficient. We have a large number of files that are not always machine reading friendly, and we also have quite a heterogeneity in data observation. Not everybody is, for example, using the same units and so on. So that's kind of a pre-processing work. The main challenges that we are foreseeing is that we will need two types of access. We'll need to access quickly to a few number of observations within a large number of them, mainly for data visualization online, like on web portals. And also we will need more access to large number of observations within a large number of them to allow machine processing and parallel processing. So for this, the solution would be for the data visualization challenge, testing the use of NoSQL databases like Cassandra. And for the data processing aspect, is more the use of data cube structures or buckets. Data cubes, you can see it as a remix cube, and the NoSQL database is like a huge Excel file. For this, we will use on-demand data processing. So we will have the need of the virtual research environment that's going to be developed and used in the Phidias project. And that's FAIRi, we will have the use of Jupyter notebooks so that we can annotate, compare, conserve, and share expertise, because in our ocean use case, we have partners from France, but also from Finland, and you cannot meet up every week. So sharing the Jupyter notebook will give more easily sharing of expertise. And the Jupyter notebook will also give us access in one environment to be able to have access, so we hope, to different data structures, so the CMEMS, CDataNet, and Argo. We will also be scripting in different languages, and this FAIRi will allow us the use of Pangeo components and Diva software. And finally, we have the quite important feature of the GIS features, so for visualization, the inputs. So seeing if in our study area, the input data is really present, or if we have to change the area or use another type of data sets. And also the GIS features more for the outputs, so that we can compare the results of different processes. So that's it. I was quite a bit fast. I hope you understood everything. Don't hesitate if you have some questions.
So thank you, Cécile. Thank you very much. Timing is perfect. So some question?
Yeah, we do actually have another question. It's a broad one for Cécile. Thanks for your splendid presentation as well. And it says, how can the development and application of big data technology support marine data research? I think you kind of already explained that, but maybe you can point out some other aspects.
Yeah, the main, we're going to say big data technology is quite a vast word. So for us, the main uses we're going to have is the data cube. So I told you it's like a remix cube. It's allow you to, for one area, to observe it from different input data. For example, compared to NoSQL databases in Cassandra, you have like an Excel table, and you have the columns and the lines. And the data cubes, for example, imagine that you have columns and lines all around your cube, so you can choose with which parameter you can go observe your environment. I hope this answers your question.
Yeah, that's perfect. Thank you, Cécile. Thank you very much. So I remind you, the participant, that we have a question and answer session at the end of this webinar. So please give us some question by chat, so that we can answer at the end of the webinar. So now it's a presentation by Alexis from CSC, Alexis Callio, about the development, the AI services targeting user communities. Alexis, the stage is yours.
Thank you. So, and hello to all on my behalf. So my name is Alexis Callio, and I'm working as a development manager for data analytics in CSC. And CSC, quick background on who we are. So we are the only computing center, national computing center in Finland. So small country has only one national center for this purpose. And we are located in Helsinki capital area, but also then our data centers are actually far into northern Finland in Kajaani. And well, we do all kinds of services, not only HPC. So that's also the kind of reason why we are here. We are working with machine learning techniques and so on. So hopefully also can help on these areas, and data management and things like that. And what CSC does in Phidias project. So our main work is in data workflows for HPC, so high performance computing and high performance data analytics, HPDA environments, and sort of we are talking about on the fly computing of data. So sort of optimizing distributed large scale machine learning workloads. That's the basic idea what we are doing on the technical development side. Then we are also supporting the ocean use case, which we just heard previously. So kind of you could say that we are partnering with CINES to especially help on the computing center kind of topics. And I'll kind of go beyond the Phidias project and introduce what we do also more briefly at CSC, or more widely at CSC when it comes to AI. So we have different user communities doing machine learning and AI related things. So especially, of course, the big capacity driven fields are important customers for our large systems, but also areas like bioinformatics, which are very much driven by data. And actually nowadays bioinformatics is the largest user group, not only in numbers as it has been for quite a long, but also in capacity usage. So not anymore physics being the number one. And then also tackling the emerging data-driven fields, so such as digital humanities, who are working with social media data and these kind of topics. So this is what we've been seeing in the recent years. And of course, we also sort of interface the research IT management and infrastructures in actually very large scale, and we are working with many different EU projects on that topic. And finally, also working with public institutions in Finland for helping them to use AI and data analytics, like ministries and such. And these kind of services we have targeted to our user communities. So of course, first AI consultation and business intelligence consultation. So usually our customers come with the question that we need some AI, and then we kind of start asking, okay, what kind of problem do you actually have, and do you have data? And then slowly we usually converge to some kind of meaningful definition of what people actually need. So that's quite a large part of our work, is defining the projects and sort of trying to figure out that what's actually needed. And then just giving general data science, machine learning, data engineering, AI, BI expertise. So running workshops, like yesterday we were running a workshop actually in northern Finland, in Kajaani, next to our data center for the local community. And then also running more traditional training courses and doing tailored consultation on these topics. Then we come to the sort of ministry funded part of our service. So at CSC we provide services for Finnish researchers free of charge, funded by our Ministry of Education. And also this will be beneficial also for Phidias project, because for the ocean use case we have a Finnish partner, so we can provide capacity easily for this project as well through Syke, our other Finnish partner in this project. So on this ministry funded side, we run training courses for those topics mentioned previously. So data science, for example, introduction to R course, and machine learning, practical machine learning course, practical deep learning course, and some data engineering topics like Apache Spark, which was actually also mentioned previously in the ocean use case. And then also help our research users in using AI and data analytics methods. So basically answer their questions about pretty much anything. So how to use our environment, or which method they should choose, or how to get their data in the right format, and so on. And then of course the other main area is then computing services, because we are a computing center originally only a computing center, nowadays a bit more as well. So we run cloud services, which are especially sort of the building platform for different machine learning frameworks and sort of higher level frameworks like Apache Spark, Apache Kafka, well, more recently Apache Airflow, these sort of data engineering tools. And then HPC computing environments for sort of more ambitious machine learning. So there we have clusters with very efficient interconnect and try to sort of enable our users to tackle really large machine learning challenges, and of course kind of also try to provide something that the cloud giants like Amazon and Google can't provide. So very sort of optimized and specialized environment for large scale machine learning tasks. And then beyond this sort of high-end stuff, we also have then the low-end services. So for easy to use services, not so huge resources provided through them, but making the entry into scientific computing as easy as possible. So we have the notebook service, which allows you to run your own environment, own virtual environment at CSC. And then also many of our services have a sort of sensitive data version of them. So for example, our cloud environment has a kind of clone of it that's in a sensitive area.
Okay, Alexi, 1 minute left, please.
Yes. Yeah, and as an example, I could mention this e-infrastructure collaboration. This is a Nordic collaboration for improving meteorological forecasting through using public or consumer weather centers. So our job is to figure out the sort of machine learning methods that will filter out incorrect data, because when you allow consumers to provide their data, then of course you will get a lot of incorrect measurements. And another example is our internal work. So we do sort of analytics dashboard for our computing server usage to figure out that what areas of sciences are. So this is slightly old screens of the physical sciences are still #1 in the research usage, but as far as I know, it has now tilted for biological sciences just very recently. Finally, I'll mention one main big motivation that we have for developing AI services, of course, the Euro HPC project and the LUMI environment that we are building. So it's one of the 3 pre-exascale supercomputers built in Europe and will be based very largely on GPUs and targeted for like very extensive machine learning tasks. So this is also sort of funnel that we would like to push also Phidias people to go into, so find ways to benefit from machine learning and then use the Euro HPC resources to actually do the task, because the system will be very extensive, like 10 times larger than our current systems, at least, or 20 times.
Okay.
Yes.
Okay. Thank you very much, Alexi. Thank you very much. Yes, LUMI is a wonderful project. Maybe we can discuss about that during the final question. So, Francesco, some questions from the audience?
Yes, I have another one for Alexi. Thanks again also to you, Alexi, for your illuminating presentation. And it comes a question that I think is a bit tricky to reply, but well, it comes either way. In your opinion, other than the clear advantages, where do you think artificial intelligence might pose major risk for everyday life of people? I think it's a big one, but maybe you can give a small insight.
Well, my standard answer to this is that artificial intelligence probably is not going to pose risks as it is, like the Terminator fears or anything like that. So I would be worried about, because it's a tool and it's a very limited tool. If people tend to forget that even if AI is good at something, it's a very limited area. So I would be mostly worried about what other people use this tool to do. So for example, what governments and big corporations might use AI. So I would see the risks in people, not in tools.
Thank you very much. Thank you very much, Alexi. And I think I can leave the floor to Boris for the last questions. We have few ones.
Yes. So maybe some participants want to ask some question. Are there questions from participants?
Yes, there is one question. Okay, the first one is, at European level, how much supercomputers and exascale capabilities are exploited at this moment? Can we consider Europe at the forefront of this field? I leave the floor to you, expert.
Who wants to answer this question? Well, I can begin. So I'm not sure that Europe is actually a leading partner of the exascale area, because in US, for example, there are 3 exascale supercomputer planned already in 21, 22. So in Europe, we are discussing about having 2 exascale machine, and normally the agenda is around 23, 24. So we have pre-exascale machine, as Alexi said just before, and LUMI will be one of pre-exascale machine. But on the HPC race, actually Europe is behind US and some kind of also China, but mainly US. US is actually the leadership, and but in the AI services, machine learning, deep learning, Europe is is powerful, because we have a very good scientific learning. We have good university, good researcher in applied mathematics. So we have bright minds in this field, but we have a difficulty to keep them in Europe. To be honest, salary are larger, of course, in US or some other place, but we have good startup, we have good SME on this field, but we are actually fighting a lot with US and China in artificial intelligence field. Maybe Alexi can give some comment on that too.
Yeah, before that, I have another small question from for Alexi. It's coming from Philippe Segers, and he's asking to Alexi, what is the meaning of the acronym LUMI?
LUMI, it's actually not an acronym. It's a Finnish word for snow, and of course it's nice that it's also kind of means light in some other European languages, or has this idea. So, but it's snow. Very popular name in Finland nowadays, also for small children. But when it comes to question about Europe and artificial intelligence, so I think the answer is exactly the same as Boris had, that on the research side we are quite good, not maybe the leader, but anyhow on the sort of on the good side, or on pushing the edge. But then when it comes to applications, then we start to lag and behind. So, and of course, but kind of the positive angle is that Europe has its own approach into data and sort of on building things on top of data. So this privacy concerned approach, and which might be considered as a bottleneck, but also as a sort of competitive edge. So at least we are not exactly kind of defining our own competition, which I find good.
Very good, very clear. I think this fully answer to the question. I mean, I have another one. Maybe someone else of you can reply. It's come from Mr. Romuald Josian, and he's asking, what are the targeted data analysis tools algorithms, like deep learning, machine learning, others? I don't know, whoever of you can pick this up.
Yes, maybe Pascal or Jean-Christophe can give some comment on that.
Yes, Pascal is speaking. I just can give a brief start, just saying that in order to address the analysis of atmospheric hyperspectral data, we start to use very simple processing, which is based on principal component analysis. And the aim is really to be in position to project the spectra measured by the satellite onto their normal variability, which is represented by principal component analysis. And then this allows us to extract the information of non-normal or extreme data. So this is a very simple way to identify. This is not artificial intelligence. And the other way is really to try to understand which kind of artificial intelligence could be used for doing that better. And this is based more on some technique to understand the underlying dynamic of the data. And this is not basically machine learning. This is more other way to be in position to make some modeling from the data. And so we could discuss that more on a later stage of that project.
Thank you very much, Pascal. You've been really exhaustive. And okay, it's 11:10. I think it's about time to close this wonderful webinar. And I want to really personally thank all of you really very much for your informative, spotless presentation. And I hope you had a nice and a good time as well. And I just leave the final word to Boris to close this up.
Yes, thank you, Francesco. Yes, thank you for to the participant, of course, because it's the first time we do that, and we will do that again and again to share the activity of Phidias, the news from Phidias. So thank you all for your participation. Thank to Trust IT, of course, because the organization was perfect, and thank to the speaker because. It's not an easy game, but I think the first attempt is good. So Phidias is working, is running. So we promise you new tools and new exciting results in coming months. And we hope to see you again in some month for the second webinar. So thank you all, and have a nice day, and see you soon.
Have a good day, all. Goodbye. See you next time.
Goodbye.
Bye-bye.
Goodbye.